Okay, so I'm back here, and the last problem we look at is something to do with the towers of Hanoi again. So this time it goes through some rules. It's well known that the optimal sort of solution for Tower of Hanoi puzzle with n bits involves 2n minus 1 moves. The optimal solution for n equals 3 is shown below, where the start is the leftmost, destination is the rightmost, blah, blah, blah. Part of an in-class lab, Roberta will hand out Tower of Hanoi steps to her students and let them try to solve the problem on her own. She goes around the room. She realizes for larger size sets, she has trouble looking at the current layout and determining whether the student is on the right track or not. In other words, she wishes to know whether or not a given configuration of the puzzle is one of the 2 to the n configurations in the optimal solution sequence. You would also like to be able to tell her students how close they are to the final configuration. Okay, and needless to say, blah, blah, blah. Okay, so they give you at most 50 disks, some configuration, and you have to figure out if it is one of the configurations in the sequence of optimal moves, and if so, how many moves are left. Okay, display no if the configuration is not in the optimal solution sequence. Otherwise, display the minimum number of remaining moves. Note that the given configuration might violate the rules of the puzzle, in which case you just output no as well. So I'm not going to say too much about this one because you can easily check if you have a larger disk on top of a smaller disk anywhere and print a no. So I'm going to assume that you just know what to do here. The more interesting problem, I guess, is how do you know where you are, right? So just as a reminder, if you don't know this before, in Tower of Hanoi, you have basically a bunch of disks. You have 3 pegs, which are called 0, 1, and 2. You have a start, which in this case is 0. You want to go to 2, and then there's some kind of a temporary working peg that you use, which is called 1. And the idea that what you do is if you have n disk, you move n minus 1 disk, the top n minus 1 disk, from start to tam. Then you move bottom disk from start to end. Then you move n minus 1 disk again from m to n. Right? So, and these two are recursive calls. And of course, when you only have one, when you have 0 disk, then you don't move. You don't do anything. Right? So you somehow recursively move this top n minus 1 disk to here. Then you move this bottom disk to here. And then you move this to here, and that's how you're done. And the total number of steps, if you do it this way, is 2 to the n minus 1, if I remember. Right, it says that right somewhere, right? Yeah, 2 to the n minus 1. And the idea is that this is going to take 2 to the n minus 1 step. This is, of course, going to take 1 step. This is going to take this much. And then when you add it all together, you will get this. All right. So now the question is, if I give you any configuration, is it one of these configurations or is it not? Well, what do you do in this situation? And this is a recursive algorithm. And the idea is basically whatever configuration that they give you, you don't actually care about any disk. You just care about where's the biggest disk. Okay, the biggest disk could be here. If the biggest disk is here, that means you are in this part. You haven't done this part yet. You haven't moved the bottom disk. So you know that to search for whether whatever you have here, right? You might have this here like this. You basically ignore this disk and ask, is this configuration that you get a valid configuration for moving n-1 disk using the same start, n, and temp? Okay? If, on the other hand, uh, you see that the largest disk is here, you know immediately that this is no good because there's no configuration in which this middle disk is a temporary. There's a bigger distance. It's always either the start or the end. So you know that it's not that. So when you see it in the middle, you know that you can say no. Finally, if you see that it's here, then you know that it's going to be one of these two steps. So you then say, well, okay, now that you do this, now you're in this state. Now you're in this state. So you have to see if you are going to be one of the possible configuration, but this time you need to know that it's a valid configuration from M to N with the start here. Okay, so it's the temp. Okay, so if you have written the recursive code for solving tiles of Hanoi, you probably will have four parameters in your recursive function, the number of disks, and these three, which one is the start and end and temp, and basically you just recursive code, make sure that you call it the right one, and then they all sort itself out, and there's no exception here. All right. So now, at some point, you run out disk. If you run out disk and you haven't got this situation where you say no, then it means it's one of the valid situations. But how many steps are remaining? Well, if you're in this part, right, then you basically figure out how many steps are remaining in this part, and then add to it this much, 1, 2 to the n-1. If you're in the other parts, if you're in this part, then of course, whatever that returns, that's your answer. So that's essentially what you have to do. You basically write the normal Tower of Hanoi solver, but then instead of actually moving a disk, you ask where is the bottom disk? Is it in the right position? And if it's not in the right position, say no right away. Otherwise, either you're in the first half or the second half. If you're in the first half, you recurse in the first half, but then you put whatever answer you get, you add 2 to the n-1 to the answer. If you're in the second half, then when you recurse, you have to make sure that you permute these peg IDs correctly. And then whatever answer you get is your right answer, it's the answer that you return. So it's kind of like a binary search in some way. And you have to decide are you in the first half of the sequence or the second half of the sequence based on the location of the bottom disk. And then then you just do some arithmetic. Okay, so the location of the bottom disk is the start peg. That means you haven't gone to the first half yet. So you're still in the first half. If the location is a temporary peg, you know the answer is impossible. If the location of the bottom disk is in the destination at the end peg, then you know it's in the second half. Okay, so I guess that's take care of the easy problems, and I will talk about the harder problems in another video later. Okay? Feel free to reach out to me if you try to translate these into code and you can't quite figure out how to do it. Okay?